Welcome to lesson 8.5, day 2 video notes. The learning target for day 2, in day 1 we were just learning to solve sides using law of sines. Today we are learning to solve for angles of oblique triangles, again using law of sines, but we have to be careful. So the reason we have to be careful, we looked at in class, we actually looked at these problems here where you tried to set some up, and we talked about the fact that when you're given an angle and two sides, one of the sides being opposite of that angle. So here's our angle, angle A, the opposite side being side A, and then side B being between them. What I have is angle side side. And remembering that in solving triangles using trigonometry, we're actually going back to proportions. We're going back to similar triangle. The trig ratios give us proportions for all triangles that have ratios similar to these. Even when we're using law of sines, those ratios within the proportions are based on similar triangles. And so we have to be careful because we don't have congruency. Angle side side and another angle side side, that's not a rule for similar triangles, and it's not a rule for congruent triangles. Whereas angle side was a rule for congruent triangles, and so we could get similar triangles that way since there would be a congruent one. So here's what we looked at. We said, well, wait a second. We went back to when we talked about why angle side side didn't prove triangles congruent. You could have angle side side where one of the angles is acute over here, and you could have angle side side where the exact same side length for side length A, now I'm going to look at the purple triangle, we have an obtuse triangle. So I could have had one triangle where this angle, angle B, was acute, or I could have this triangle, the purple one, where B prime is obtuse. So when we are given an angle and two sides, and it's in the order of angle side side, we have to be careful because there could be up to two triangles. It's also possible that there is only one triangle, and so as we go through the math, we'll see what happens when there's not any triangles or when there is one. The formal reasoning for why there would be no triangles or just one triangle is a little bit more complicated in terms of equations, and we usually take careful time to explore that and detail that in pre-calculus. For now, you're going to go through the steps and realize, wait a second, these answers aren't making sense, so that there's either not a triangle or there is only one triangle. So let's start with this first problem. We're going to draw the same picture that we have over here. We have an angle, 38 degrees for angle A. We have side A being across from the 38 degrees being 8, letter B being 10. So now it is possible, or maybe it's not, but I'm not going to get into that today, so right now we're just going to do this, that this could be an equilateral or isosceles triangle here being 8. So right now B is 10 and angle B is across from that 10. And I'm looking at the brown triangle. But it is possible that I have instead an obtuse triangle, or maybe in addition an obtuse triangle. So I have to also find a case for B prime, which means angle C will either be this whole angle or angle C prime will be just this little sliver. But we're going to find angle B first in doing this. So let's look at this. We have sine of angle A. Sine of A is 38, sine of 38 over side A is 8. So this is all for angle A. Now based off of angle B, for angle B, I'd have sine of B over 10. We have our proportion, sine of the angle over its opposite side, sine of the angle over its opposite side. So right now I'm just solving the brown triangle. That's why I'm calling it angle B, not angle B prime. And so in doing this, I'm going to cross multiply. This is going to give me 10 times sine of 38 degrees equals 8 times sine of B. And our job is to solve for angle B. So we're going to divide by 8. We now have 10 times the sine of 38 degrees divided by 8 equals the sine of angle B. Well, if the sine of angle B is this ratio, by the way, there's a ratio within that ratio, then the angle, to find the angle, we have to use the inverse. So the measure of angle B will be sine inverse, we'll use that to get rid of this, of the 10 times the sine of 38 degrees divided by 8. So in our calculator, we have 10 sine of 38 divided by 8, and I don't want to do that. I'm actually going to come back to the beginning because I forgot to do in sine inverse. Sine inverse of 10 times sine of 38 over 8, close parentheses. And this gives us 50.3, which rounded to the nearest degree is 50 degrees. So the measure of angle B is 50 degrees. So now I have the measure of angle B, and in this brown triangle, if this is 50 degrees, it's very easy for me to calculate the angle C. That means the measure of angle C would be 180 minus 50 minus 38, which is 92 degrees. And then to find angle C, I would do sine of 92 over side C, actually not angle C, side C. Angle C being, if I'm doing the regular angle C being 92 degrees over C, equals, I'll go back to sine of A, sine of 38 over 8. And here it's just as it was the first day of this lesson where I cross multiply and I'm going to divide to get C by itself. So I'll actually have 8 times sine of 92 degrees equals this times C, and so I'm going to divide to get C by itself by dividing by sine of 38. So to find side C, I have 8 times sine of 92 divided by sine of 38, which gives me 12.986, which rounded to the nearest hundredth would be 12.99. Side C is 12.99. However, that's assuming that we're dealing with the brown triangle. And maybe that is the only one that exists. We're going to see in a second. But it is possible that maybe another triangle exists when we have the angle side-side setup. So now I need to also solve this triangle. Here is C prime and A and B prime. Well, here's the thing. If this angle were 50 degrees, which we did find it to be 50, it is possible that there's this isosceles triangle in here, making this the other 50 degrees, which means that this angle B prime, because B is 50, B prime would be 180 minus 50, which would give us 30 degrees. So that'll actually give us 130 degrees here for B prime. So we already know B prime is 130 degrees. We know A is still 38. This side, B prime, C prime is 8, just like BC was. There's the isosceles triangle. And now we just have to find C and C prime. Well, C is, once again, easy to find because I just do 180 minus those two angles. 180 minus 130 minus 38 is 12 degrees. So since we got a positive angle for C prime, it looks like it is possible to have this triangle. So now we have that C prime is 12 degrees, which means, hey, there's our other case. We need this lowercase c prime. We need to know what side length would go with the 12-degree angle. So we're going to do sine of, again, A is the first one, the one that was given is the one we always try to go back to, 38 over 8, 38 degrees over 8, equals sine of c prime, which in this case is 12 degrees, over c. And we're going to cross multiply, so we're basically going to multiply these two, and then that times that to get it by itself. We're going to divide by sine of 38. So we're going to do 8 times sine of 12 divided by sine of 38, and we get 2.701, which is 2.70, or 2.7, but it says to the nearest hundredth, so I'll put that there so we know that we actually did. So there are the two possible cases. There are sometimes two possible cases. When you have side-side angle, there will either be two solutions, one solution, or no solutions. If we had more time, I would go into why that is the case. You'll get there in pre-calc and you'll see why it works and why it doesn't. But I'm hoping that at least you can understand why, when we go back to angle side side, how it's possible for this side to pivot inward and create an obtuse triangle instead. In some cases, it won't always be the case. So there's two different case results for this. There's case 1 and case 2. Case 1, it's an acute triangle, or well, angle B is an acute angle. It ended up being an obtuse triangle. Case 2, angle B prime is angle B is actually an obtuse angle. Let's take a look at letter B. On letter B, we're going to have the same setup because, again, we have an angle and its opposite angle and then a side between them. So when I draw this, I'm going to draw it like that last one. Here's A, 61 degrees. Here's side A, 9. Here's side B, 11, and angle B. And side C, or sorry, angle C and side C. Well, because it's angle side side, if it's that way, side side angle or angle side side angle or angle side side, I have to account for the fact that there could be another case in which this side, B prime is C, and then I'd have to find B prime's angle there versus B's angle here. We begin by finding the case where B is an acute angle using just regular law of sines. So here's case 1 if it exists, and then we'll look at case 2 if it exists. So case 1, we have sine of 61 degrees over 9 equals sine of B over 11. We're going to, so all I did was sine of the angle over opposite side, sine of the angle over opposite side. When I cross multiply, I have 11 times the sine of 61 degrees equals 9 times the sine of B. Well, that's great, except we're trying to find the measure of angle B, so we need to get that by itself first by dividing by 9. So 11 sine of 61 degrees divided by 9 equals the sine of angle B. Once again, we're trying to find the measure of angle B. We know the ratio for sine of angle B is this, whatever this number is. But we don't want the ratio of sine of angle B, we want the measure of angle B. So we have to get rid of this sine by doing sine inverse. Sine inverse of this would make the sine go away. Whatever you do to one side, you do to the other side. So in my calculator, I actually need to do sine inverse of 11 times the sine of 61 divided by 9. So sine inverse of 11 times sine of 61 divided by 9, which I'll be honest with you, we go through this and do these steps in pre-calc, and we show them why it works and how and when you're going to know based on the numbers. Most students still do it this way because they just don't want to memorize all of the rules that are going into when it works and when it doesn't. So I do this and I close my parentheses, I plugged it all in correctly, and I'm getting an error, a domain error. For some reason it's not working. Well, let's take a look at why that is. Let me do this without the sine inverse. Whoops. Sine of 61, 11 times sine of 61. This is 1.06. Just this ratio right here is 1.06. Remember from your unit circle the maximum and minimum values of sine. Sine can only fluctuate, where did my unit circle go? Sine can only fluctuate between -1 and 1. And as we rotate through all angles, even greater than 0 degrees and less than 0 degrees, that value of sine has to be at most 1, and at the output for sine has to be at most 1, and at minimum -1, so that when we do sine inverse, we can match up to one of the angles on here. Well, we're doing sine inverse. Sine inverse only works if the input is between -1, or this is the ratio, not the angle, and 1. Well, sine of 61 is fine, but when I put all this together, I'm getting 1.06 something in there. I can't do the inverse of that. So that's why it's not working mathematically speaking, the limits on the domain of sine, the angle, or the range for the ratio of sine. So anyhow, what we found was that there's an error. So in this particular case, and here's the reason why there was an error, but in this particular case, there's actually no solution. So we really don't have to spend any more time on this problem. There isn't going to be a single triangle that we can create with this angle and these sides. What's happening is when we lock this 61-degree angle for whatever these ratios are over here, and this is 11, this 9-inch side over here can't swing back. It's too short to swing back to connect, and so it can't connect. So this is why on this one, there is no solution. Let's take a look at letter C and see if we get no solution or one solution or two solutions like we did for letter A. In letter C, I'm going to draw my triangle over here so that I can do my work in that space. Angle A is 94 degrees. Side A opposite of angle A. I could call these letters anything, but right now we're calling them A, B, and C. Side C is 12. Well, I'm going to call that side B. Well, I'll call it side C, but I'm going to put it here because it's still an angle by two sides. And for my picture, I want to set it up in this way. So now I'm going to be finding C and C prime first. So this will be B, this will be C prime. If you want to change the letters, you can just change them back at the end. I could call them X, Y, and Z, or any letters at all. This angle is opposite of its lowercase letter. If I have an angle and two sides given, I have to be careful. I have to account for the fact that this could happen. So this C replaces side B from what our previous picture, and angle C across from it. So this was C prime. So I'm going to calculate the brown triangle first. I've got the sine of 94 degrees, sine of the angle over its opposite side, equals sine of the angle, wait, side C is 12. Sine of the angle over its opposite side. So that's just law of sines, nothing strange there. Cross multiply, I've got 12 times the sine of 94 degrees equals 15 times the sine of angle C. Our job is to find out what angle C is in this brown triangle. We're not finding C prime yet, just C. So I'm going to divide by 15. This gives me 12 sine of 94 degrees in parentheses divided by 15 is equivalent to the sine of the measure of angle C. I'm solving for angle C. So to get rid of sine, I have to do sine inverse of 12 times the sine of 94 degrees divided by 15 to get the measure of angle C. So I put this in my calculator. Sine inverse, 12 times the sine of 94 degrees divided by 15, close parentheses, and lo and behold, I get an answer of 52.9. And this is an angle, so I'm going to round to the nearest degree. That would be 53 degrees. So for this triangle, measure angle C is 53 degrees. If this is 53 degrees, that means the measure of angle B, using the 53 and the 94, and triangle sum theorem, 180 minus 53 minus 94 is 33 degrees, which now allows me to solve for side B, because opposite of that is side B. So sine of 33 over B equals, we go back to the original angle and side given, sine of 94 degrees over 15. We're going to cross multiply, and then to solve for B, we'll have to divide by sine of 94. So 15 times the sine, 15 times the sine of 33 degrees divided by the sine of 94 degrees. This gives us 8.189, which is 8.19. So B is 8.19. That's one possible solution. Now maybe it's the only one, and I'm thinking because of this angle and the setup of this problem that it is, but we're going to go through the steps to find the second one, because you don't know the test to figure out when it's going to be and when it's not. So we're going to look at a possible case 2, where C prime, instead of C being 53 degrees, it would be its linear pair at this equal angle of the isosceles triangle. 180 minus 53 would give us the 127 here. So case 2 is where measure angle C prime is 127 degrees. Well, I know already we have a problem with that. Some of you might too. If you don't, you're going to go through the steps we just did, like this, except it'll be 12 times, it'll be sine of 94 4 over 5 equals sine of c prime over 12, and it's not going to work. Why is it not going to work? Because in this triangle I have a 94-degree angle and a 127-degree angle, and that means that I have two obtuse angles, which means angle B would actually have to be negative. And that's not possible. The triangle sum theorem says the three angles have to be positive and have to add up to 180. So because of the measure angle A being 94 and those two both being obtuse, there is no case 2. There is no obtuse triangle. There's only one solution, where C is 53 degrees, B is 33 degrees, and side B is 8.19. Please try to set up these triangles for D, E, and F. See if you can figure out which ones have one solution, no solutions, and two solutions. You may need to completely solve the problem to get there to see if you get the errors in your calculator. We will have the answers to go over tomorrow in class after you discuss them in groups. Have a great day.